All right, thanks everyone for attending my presentation. The topic of my paper is the structural breaks in seemingly unrelated regression models. So as we know, many macroeconomic and financial data sets are subject to structural breaks. So in the case that we have break, if we assume that this is the full sample of observation, and if we have breaks at time t1, t2, up to tm, because of these breaks, we have different set of parameters, slope parameters, and also variances. So if we wanted to turn this to the regression model, this is the model that we have. So these are the breakpoints T1, T2 up to Tm, and they have allowed the break that affect both the slope coefficient and also the error variance. So here I, in this notation, I represent the number of individual firms, countries, and T stands for duration of the time. Now, the question is how to estimate the parameters under this setup. One common solution is to use the observation within each regime. So basically, we pull the observation across individual and use only the observation within each regime separately to estimate the slope coefficient. But one problem with this method is that if the number of observations within each regime are small, then the estimator will experience a high variation. We can think about the structural breaks model as a model uncertainty, and this uncertainty appears because we don't have any information about the size of the break. We don't know whether we have a small break, we have a large break. So if we had this information, for instance, if we know that the size of break or magnitude of the break is small, maybe if we ignore it and use the full sample of observation, this results in better estimation and as a result, better forecast. So, but we don't have this information. So this is somehow model uncertainty. And the way that we can deal with this uncertainty is either we can do model selection that it's actually known as pre-testing, that we do the test, and based on the result of the test, we choose which estimator we need to use. Or another way is to do the model averaging, that we take average over a series of models. And another method is the shrinkage method, that it's the like a model averaging when we have only two models. And the shrinkage method is the one that I use in this model, in this paper actually. So basically this method allows for uncertainty emerging from both model selection and estimation, and it allows for modeling heteroscedasticity and cross-sectional dependence, which is the interest of this paper. A little bit about the literature review. We can say that the literature review in this area, it's divided into two streams. The first stream of the literature, they focus on detecting the breakpoints under panel data model. It backs to by 2010. We have actually many great contributions in this area that I have listed, some of them here. And the second stream is related to the forecast improvement, that given that we know that we have break, now how we can improve the forecast, how we can have a better forecast in this area. These are the papers related to the forecast improvement, and all of them are in Bayesian framework. Okay. So the question that I wanted to answer in this question is one, how to improve the estimates within each regime. By improvement, I mean in terms of having lower mean square error. I'm going to do that by using the neighboring observations. And the second question is, I wanted to know how to improve forecasting in the sense of having lower mean square forecast error in Shor models under structural breaks. Here is the model. So we have a heterogeneous linear panel data model, and the slope coefficient as divided into two parts because of this break that has happened at time t1. And for simplicity, I'm showing you the result for a single break case, but the extension to multiple break is straightforward and it's available in the paper. So we have a break at time t1, and x is a k/1 vector of regressors that it may contain lag value of phi t, and u is the error term with cross-sectional dependence. And in this paper, n is fixed, and we have large t. So here I have stacked the model over time and individuals. So capital Y is the notation that I will use. It has the information for all of the individual units, the dependent variable. And notice that each of these Y, I, it has two parts. And here is the block diagonal matrix of X. And this is the slope coefficient that each of them, again, it has two different values. And this is the error term. So some assumptions that I made, the first two assumptions I made in order to have the central limit theorem to be held. And the third assumption is related to the error term, that we have cross-sectional dependence. So basically, individual I and individual J are correlated with each other. So we have variance heteroscedasticity across the regime, but over the time, they don't have any correlation.
Okay.
And here is the estimator, the sign-like shrinkage estimator, denoted by B hat W. And this is the combination of two different estimators. One of them is the unrestricted estimator, that the unrestricted estimator is actually, it's using observations within each regime separately and then estimate the slope coefficient. So this is going to be the consistent estimator, but it is less efficient because it drops some of the observation. And the other one is the restricted estimator. So the restricted estimator, it just uses all of the available observations in the sample. So basically it ignores the break. So in the case that we have break in the model, this estimator will be biased, but this is the efficient estimator. And the combination weight W, it depends on this square loss function, that basically this dt, it measures the magnitude of the break. So if we have a large break, then it means that we have a large value for dt, then the combination weight will assign more weight to the unrestricted estimator, which is actually consistent one. But in the case that we have a small break, then the combination weight assign more weight towards the restricted estimator in order to gain from its efficiency. And here, this square loss function, we have the weight W here, that this W, it can be any positive definite user-specific weight. For instance, if we set it to equal to I, then it becomes the unweighted loss function. We can set it to the inverse of variance of the unrestricted estimator, then it becomes the wall type statistic. So I have solved the model for any form of W. And tau here is the shrinkage parameter. It's a positive parameter that later on I will derive it from minimizing the asymptotic risk. All right, so this is the unrestricted estimator that I'm using GLS to estimate that. And here is the restricted estimator, that R is the restriction matrix with rank P. So for instance, if we wanted to put the restriction that there is no break, then R has this form. So at the end, you can see that the multiplication of R multiplied by the slope coefficient, and then it has this form. So basically, there is no break for any individual. So it's ignoring the break. And in order to derive the asymptotic distribution, I'm using the local alternative assumption. So basically, if we assume that this H is showing us the break size, then it means that as the sample size increases, we will have a weak break. And one thing that I need to mention, I have allowed the break size to be different across the individual units. So if you have break, it doesn't necessarily have to be exact the same size across the individual units. All right, in theorem 1, I have derived the asymptotic distribution for the estimator. So here we have the asymptotic distribution for the unrestricted estimator. And here is the asymptotic distribution for the restricted estimator, which has bias. The bias is this H. So if it's H is 0, so basically if there is no break in the model, then this part will be gone and this estimator will be consistent again. And because the combination weight, it has some random parts, so I derived the distribution of the combination weight, and by having all of this, finally we are able to derive the asymptotic risk for the Stein-like shrinkage estimator, which is a nonlinear function of random vector z, and also it depends on this magnitude of the break. Now, by having the asymptotic risk, we can derive the asymptotic, by having the asymptotic distribution, we are able to derive the asymptotic risk for the Stein estimator. And here is the asymptotic risk for the Stein, which is less than or equal to the asymptotic risk for the unrestricted estimator minus this term. So the unrestricted estimator was the one that it uses only the observation within each regime. Now, in order for me to have a better risk for the Stein compared to the unrestricted estimator, I need this term in the curly bracket to be positive. And this is positive if tau star optimal is p minus 2, number of restriction minus 2. And finally, by plugging this back into the risk function, this is the final look for the asymptotic risk. That's basically it's saying that you can think about this parameter C as a break size. So basically it's saying that if the break size is very large, then this part will be gone, and we expect to see the equal performance for the Stein estimator and for the unrestricted estimator. But for the cases that the break size is small, then this term will be negative, so the risk of the Stein will be lower than the risk of the unrestricted estimator. And these are the cases that we are interested to see. But the summary is that we never see the underperformance for the Stein estimator relative to the unrestricted estimator. So in the worst case scenario, it will perform equal to the unrestricted estimator. Now, we can also use this estimator in order to do forecast, because for the forecasting part, the parameter that enters the forecasting period is the slope coefficient in the second regime. So I'm using this selection matrix G to only focus on the slope coefficient in the second regime. So I'm multiplying this selection matrix G to the estimator, to the Stein estimator, and I'm able to derive the mean square forecast error for that. So this is the weight for one step ahead mean square forecast error. And in theorem 3, I showed that the mean square forecast error of the Stein estimator is less than mean square forecast error of the unrestricted estimator. And again, this term, it depends on the break size. So for a small break size, we expect to see the outperformance of the Stein relative to the unrestricted estimator. Now, let me just show you some Monte Carlo simulation study. I will explain the specification in figures. Just to mention that I will report the ratio of the mean squared error, and the ratio of the benchmark model is the unrestricted estimator. So I report the ratio of the Stein estimator over unrestricted estimator, pretest estimator, which is the model selection, pretest estimator over unrestricted estimator, and also I'm reporting the results of the minimal mean square error estimator, I denoted by beta hat gamma in the paper. That basically this estimator is combining the unrestricted estimator with the restricted estimator with a weight gamma between 0 and 1. So I have the theory, everything in the paper, but in the interest of time, I've dropped this in my presentation, but I will show you the result of that. But one thing that I notice is that by driving the risk, everything of this estimator, I noticed that this estimator actually is in the class of the Stein estimator. And these two estimator, I mean, a Stein estimator and the minimal mean square error estimator, they always perform better than the unrestricted estimator. I mean, if the number of restrictions for a Stein is greater than 2. And I have theoretically proved that the Stein estimator also always outperforms the minimal mean square error estimator in the sense that it has a lower risk. Now, here is the result. So this is the result for the case that breakpoint is at 20. So basically the pre-break sample observation, we have 20 observation, the post-break, we have 80 observation, number of sample size is 100. And we have 5 individuals and a number of regressor is 1. The vertical axis, we have the relative mean square error, and horizontal axis shows the break size in the mean, which varies up to 1. And I'm reporting the result for the unrestricted estimator, which lies at line 1, because this is the mean square error of unrestricted estimator over the unrestricted estimator, and assigned with blue line, minimal mean square error estimator with green, and finally the pretest estimator with red. And figure A is for the case that Q is equal to half. Q shows the ratio of the break in the error variance. So when Q is half, it means that the pre-break sample observation is less volatile compared to the post-break sample observation. And we have the opposite in figure B. So at first glance, by looking at this figure, we can see that both the Stein estimator and minimal mean square error estimator, they uniformly perform better than the unrestricted estimator in both figures. And as the break size increases, they perform very close to each other and also close to the unrestricted estimator. The pretest estimator, it performs well when the break size is very small. So basically when we are at the beginning of this figure here, a small break, or when we have a large break, so the test can detect the break correctly. But other than that, it has some sort of overshooting. And if you look at the figure B, we can see that the outperformance of the Stein or the minimal mean square error estimator compared to the post-break estimator is even higher compared to figure A. So the reason is that here the Stein is combining the unrestricted estimator with the restricted estimator. And because for this specific setup, when the breakpoint is at 0.20, then the pre-break sample observation by itself will have a poor estimation because there are not enough observation in that. Now, when we combine it with the restricted estimator, if the post-break sample observation is less volatile, which becomes figure B, then the Stein will gain more compared to the case that the post-break sample observation is more volatile. So that's why we see a higher outperformance in this figure. And
Shahnaz, I hate to interrupt, but it's 5:20. So if you can wrap it up in 5 or 10 minutes, because we won't have the last speaker, that would be great.
Sure.
Go ahead.
Okay. And here is the result for another specification when breakpoint is at 80. So again, similar result is hold. Now, for the empirical analysis, I applied the method in 2 different data sets, one forecasting US inflation rate for 7 industries listed here. And also I applied this for forecasting real GDP growth. And regarding this application, I used the monthly data from this range, and the predictor is the industry level industrial production. And I estimate the model using initial estimation period of 5 years and recursively generate out of sample forecast for the inflation rate. And I'm reporting the mean square forecast error for different methods. So here is the result. This is the result mean square forecast error for the Stein estimator, for the minimal mean square error estimator, unrestricted estimator. Here is for pretest estimator, and finally here is the mean square forecast error for the unrestricted estimator, which it actually ignores the cross-sectional dependence. So it only take each series separately. So if we compare the result, we can see that both of these estimator, Stein and minimal mean square error estimator, they have an outperformance over the unrestricted estimator, and Stein is the best one. It has a lower mean square forecast error. And to see whether this outperformance compared to the other methods is statistically significant or not, I am reporting the Diebold-Mariano statistic. And here the result shows that the outperformance is statistically significant at 5% or 10% significance level. And I actually applied the method for forecasting real output growth in G7 countries, and we have the similar result. The Stein outperforms other method, and the outperformance is statistically significant at 1% significant level. So in this paper, to conclude, I propose a Stein-like shrinkage estimator and minimal mean square error estimator, and I prove that both of them uniformly performs better than unrestricted estimator over the whole parameter space. And I show this outperformance in simulation and also in empirical examples. So that's all. Thank you.
Perfect. Thank you, Shehnaz. This was wonderful, but we are a little beyond 5:20. So I'll get rid of my talk, and then if people can stick back a little bit, we can have questions. Our last speaker will not be available, so we can use the rest of the time from 5:40 and beyond for questions. So let's see whether we can bring my PDF up. Where do I go? Oh, that one probably. Can you see the screen, Shehnaz? Good. Okay. So yeah, in case you have joined lately, recently, one more time, I am Moinag Bhaduri, an assistant professor in the math department, Bentley University in Massachusetts. And I am, in just a little while, going to describe to you a way in which you can forecast reliably a temporal pattern where you know there could be structural breaks from the very beginning. I normally work on change detection problems in a continuous time point process. And today I have to describe to you a crucial subclass of it, the self-exciting subclass, where one event triggers or untriggers several others in a very close neighborhood. Several natural and artificial phenomena, they fit this premise, they fit this context. Very often we find, for instance, a major earthquake causing several aftershocks. Gang violence or terrorism could be another example where very frequently, again, a large attack as if causes several retaliations over the next few days. So through this work, it's trying to check whether changes have happened, both in the way the major events and the minor events emerge as time goes on. I need to quickly take you to the way these stories are normally modeled. We usually assume that there is a nice mathematically tractable function called the intensity function, shown here through lambda, that controls the instantaneous probability of observing at least one event over a very small period of time. Now, knowing the intensity function is not enough to describe the system entirely. We must also know something about the underlying law, the distribution. So if that law happens to be Pearsall, meaning if the probability of observing a given number of shocks by a given time period is expressed according to that Pearsall expression, then the entire process will be a Pearsall process. And this is how the intensity enters the system as the rate of a Pearsall variable. So through this work, we are trying to ask questions about the properties of the underlying lambda function, of the intensity function, especially whether it's a constant function independent of time. Graphically, that would lead to this conic flow of shocks. Intervals of the same length are likely to contain the same number of shocks, regardless of where you are on the time axis. On the other hand, if your intensity is increasing, then as time goes on, you'd expect more and more shocks. Your process will be a deteriorating sequence, right? So the underlying lambda function, the intensity function, and the distribution teaming together drives the entire mechanism. So that will be a null assumption. As our alternate choice of the underlying intensity, we found that this expression, shown here through equation 1, does a very good job at describing the self-exciting property, where through the first piece, the blue piece, you describe major events, the first generation events, the major earthquakes, if you please, emerge as time goes on. And the green function, the second piece, describes how your minor events emerge as a function of time. You'll find that this is a data-dependent intensity. These Y values represent the times at which these events actually took place. And depending on your choice of the green memory kernel, you'll have different interpretations, different understandings of this forgetting the past property. One very choice of this green kernel is the exponential choice, where a high value for beta will tell you that you're forgetting the past very fast. Your memory decays very rapidly, while a very low value for beta will tell you that you have a long memory. Now how much history is relevant to your problem, how much history is worth recalling, how much history is worth forgetting, that is controlled by this window of size R. And here we are working with the most general framework of an infinite past, of an infinite history that leads to a Hawkes process kind of a structure, okay? So it's, again, through this work, we're trying to check that the changes have happened in either, or maybe in both colors, both the blue and the green, as time goes on. In the context of the gang violence example, a change in the blue function could probably mean something that is external or exogenous to the system. Maybe some kind of a political regime switch or the appointment of a new police sheriff in town, whereas a change in the green because of something internal or endogenous to the system. Probably you lost the desire to seek revenge because of an attack, which may have got nothing to do with the appointment of a new police sheriff in town, okay? So here is one quick simulation graphic that tells you what kind of intensities could lead to what kind of data. To your left, you have data independent deterministic intensity, something that you can write out prior to observing your data set. And you would notice that a spike in that kind of an intensity create clear crowding, a clear clustering, for this case to your right. Whereas on the right-hand side panel, you have a data-dependent random intensity, very similar to equation 1 that you saw previously. But the first generation change was placed at around 50, at around time point 50, and the second generation was around 75. And you would admit that the clustering here on panel 2 is not as vivid. It's not as clear as the one to your left, which makes this a harder problem, a harder detection problem, a harder change detection problem. So again, through this work, we're trying to look at the top panel, the data panel that is, and we're trying to infer, we're trying to guess whether changes, drastic changes, statistically significant changes have happened in the bottom panel in the way the intensity goes as a function of assuming there is a change at all. And one way to do that, one way to solve that question, whether there is a change at all, is through the first function, the z function that you see over there. It's extremely well established in the literature, known to lead to quite a few optimal tests. It's defined through a log function, a linear combination of the logged time ratios. The TIs represent the times at which these events happen. Another option that you can use is when you use the same structure, you keep the same log structure, but you simply switch the ratios about 1, okay? So Z and ZB, they're exact opposites of each other. And because of the way log functions work, it isn't hard to show that a deteriorating sequence will inflate the value for ZB and will deflate the value for Z, okay? And in more recent times, we have worked with the maximums and the minimums of these two versions, R and L. We found that they have quite good classification power. And now we're trying to check whether some of that classification power will translate to a harder scenario for self-exciting intensity. So this is an answer to that question. They're basically a 3D power study where along the wall, along the z-axis, you have the probability of correct classification. This percent, for instance, tells you that if you give me the pre and post change beta parameters from that combination on the floor, then you will correctly identify a self-exciting process, the self-exciting process 40% of the times, okay? You would also notice that along the diagonal on the floor, when the pre and the post change parameters are very similar to each other, that represents the diagonal, we have a valley in this power mountain, which is expected because around those times, detection is very, very hard. It's very difficult, which is why we have a valley in those power mountains. But on the edges, when the pre and the post change values are very dissimilar, they're very different, detection is easier, which is why the power mountains are so very steep around those points in time, okay? So that is interesting because the more recent test that we propose, based option, it's occupying the most space viewed from the top. But the troubling observation here is we have no symmetry about the diagonal. We have an asymmetry, which means we cannot shut our eyes and choose one option and use it all the time, regardless of the context. And even then, even if we could, this exercise just answers the first question. It tells you whether we have a change at all. It won't help you pinpoint the location of the change. So our proposal to do that is conduct a sequence of tests using one of the four statistics that you saw, Z, ZBR, or L, repeatedly. And if there is a test that sits on the first set of, let's say, 18 observations and says that things are fine, we have a homogeneous process, a stationary process. And if a similar test on the first set of 17 observations, one more tells you that things are not fine, we have a change somewhere in between the 16th and 17th observation, okay? There are a few technical ideas that you have to be careful about because you're doing a sequence of tests, your probability of type 1 error gets inflated, so you have to control the false discovery rate. The problem with a null set, if you find no changes at all, what's your convention? But barring those, this remains the overall idea, okay? So the next thing we did was we tried to check whether this algorithm is any good through a few real examples. Let me take a look at the time. Okay, doing good. The first example is from finance, where and for both these examples, we did a goodness of fit test prior to applying this machinery to check whether the self-exciting assumption is at all valid. Here is a data set that you time-based data basically on economic announcements that are likely to cause different types of impacts on different types of markets. It's quite a large data set, and we have focused on 3 different types of announcements: the high importance, the medium importance, and the low importance categories, only on the United States. So if you apply the change detection algorithm that you saw with those 4 proposals, your answers will be these vertical strips. These would be the most likely location of those changes, these separators. So the message from this is the number of change points you find our way doesn't have to be bounded. It correlates very often with the size of your data set. The more data you have, the more prone you are to finding more changes, more of these separators. This is quite unlike some of the other competitors we currently have. Another example I looked at was the global terrorism data, which again is quite big, which is why I've sampled 3 violence categories, and again within the United States. The estimated change points here are more visually acceptable. Our best guesses would be the times at which we have sharp edges and bends. Historically, these are times we can accept too. These separators, for instance, represents the 1970s when bombing was quite common in the United States. Change points from these armed assaults are placed in somewhere in the more recent past, which again appeals to intuition. If you look at the protests that were happening nowadays a few days ago. So in both those examples, you found that the colors are thoroughly mixed up. There is no uniform agreement about the pattern, which begs the question, which tools to trust when, which one of those 4 options that we saw, which one do we use when? So for that, to answer that question and also to understand how all these stack up against established competitors, we will look at a little more theory, and we will recollect a few ways in which you can do change points without using the sequential approach. So this general problem of change detection has been attacked from several fields, especially since the 1950s. One construction that proves to be extremely useful was the one introduced by Hawkins and others in 2003, where with a given sample size, they have translated the entire problem into finding several of these 2-sample statistics, these DKNs over here, measuring the difference between the pre-change and the post-change pieces for a fixed initial guess of K. Now, the best guess of K would be the one that minimizes some overall loss function, or one that maximizes some overall utility, for instance. And there are different ways of choosing these 2-sample statistics. In the interest of time, I won't go into details, but I will indeed point you to a beautifully written review article by Trong, where every choice is explained along with the logic behind every single choice. So here is a simulation experiment, a simulation study that answers how good you are, our 4 proposals are, in relation to the rest. The first 11 would be from the computers that you just now saw on the table, but different choices of DKNs. And notice that here the real changes were placed again at 50 and 75. That represents the first generation change, the change in your blue kernel, and the green change is at around time point 75. Those are the 2 dashed lines, the broken lines. Notice that most of our competitors, they are here towards your left. There are too many false alarms. Each dot represents a time at which you found a change, as if. So for most of those proposals, we have loads of observations over here prior to the real change actually happening, which are definitely false alarms. We are not doing that. We are L, R, Z, and ZB. We are not doing that very frequently. And also on top of that, these are the options, our four over here, 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 and here, are the options where you have the strongest and the most clearest right skewed clustering after those two very points, the true change points, okay? So this experiment was done with a fixed sample size in mind. One natural worry is what happens if you have a progressively increasing, like a large sample size, a progressively increasing sample size, very similar to the finance example, or very similar to the terrorism example. So this graph would help you answer those types of questions somewhat. So in here, we are not so much worried about the location of changes. We are more worried about the number of changes. K represents the actual number of changes. Here for the simulation study, K was set to 2, and we are trying to check whether the probability of detecting the right number of changes approaches 1 asymptotically. So we found that for most of our competitors, they are here. Those long-run probabilities are going down very fast, while for most of our proposals, we are here on this bunch. Although we are not reaching 1 very fast, but we are not dropping either, okay? So this tells you that if you stick with our proposals, the 4 recent techniques that you just saw, then if you wait sufficiently long either in terms of time or in terms of observations coming in, you will pick the right number of changes. You won't overcount or you won't undercount, right? So once you find out the true location of these changes, you can measure the distance between 2 countries' change point patterns, the change point sets, that is, through loads of distance metrics. The Hausdorff could be one choice. And this heat map to your right, for instance, tells you that according to that metric, Indonesia's financial announcements, they mimic the United States very, very closely, because predominantly we have a cold patch. The 2 change point sets are very, very similar. Or you could cluster countries too. You could put countries with similar change point behaviors on branches of a tree. So you can transfer statistical inference from one leaf to another leaf, from one country to another country. There could be some kind of correlations there too, okay? In recent times, there are loads of papers. This is very similar to what Shahnaz was talking about just a moment ago, about once you find out the locations accurately, you can put different regime models within those pieces. So your overall forecasts accuracy will be better, will improve. This paper, for instance, tells you how you can prove it, how you can validate that through tinier forecast intervals or through better accuracy metrics. So the change point work that you just now saw, it helps you answer the first question accurately. It helps you resolve the regime definitions. So you can then answer the second question: what kind of inter-event distributions, what kind of models could you build within those regimes? So the future questions become more tractable, right? So, I mean, that's really all I had for you today. In conclusion, we found how a small change in the way time normally flows from the left to the right to the left, the change from Z to ZB, that is, can trigger lots of useful statistics, like the maximum of those two, the minimum of those two, and in turn a fresh algorithm based on multiple testing that can detect changes in the self-exciting property without sounding too many false alarms. This approach is quite distribution free. Never did we assume that we have to have at most 1 change point, which most of our competitors do, the AMOC assumption. Because for us, as soon as we find out a change point, we can restart the algorithm afresh to find out the next, if any, okay? This is very fast. This is not computationally heavy at all. And if you figure out those change points, then you can use whatever favorite inter-event distributions you have in mind. Exponential could be one choice to forecast future observations too. So your question 2, question 3, or question 4 becomes easy slightly once the boundaries are defined, right? Some references. The first describes this algorithm in greater details. That's my dissertation. If you haven't, please take a look. It has more details about all this. And the last would be, this one, 1995 paper, would be all about multiple testing, which is a crucial tool that we are using throughout, right? So that's all I have. Thanks for listening. In case you have questions for either Shahnaz or I, then we will be happy to answer those. What I can do is I will stop sharing and I will put this, let's see. Let's do a quick search on our third speaker is still not present. So the third talk that you have on a dynamic model averaging in the presence of structural change by Elisa Yusupova is not going to happen. Questions, comments from anybody?
I do have a question for you.
Yeah,
thanks for your great talk. It was very interesting. Does your algorithm needs to put some restrictions for the number of observations within each regime in order to detect them, or there is no restriction for that?
No, that's a very valid question. So I briefly touched on this. The algorithm that we are running, those are in batches of 50. We found that to find out the null distribution, it's computationally very taxing. But the good thing is you have to do that only once, because the null assumption is just the fact that you're stationary. We are not specifying the stationarity at some level. We are not saying that you have to be stationary at level 2 or at level 3. And you can understand the reason why that is such a good thing here is because of the way the Z functions are defined. You would notice that even if I had said that this intensity is 1 as opposed to 2, or 2 opposed to 3, it won't make too much of a difference because those things will be canceled out. That's just a hand wavy way of proving it. That if events are happening twice as fast, it won't matter too much. This value for Z or ZB will not be affected. So no, to find out those null distributions, we have to do all this experiment only once. We don't have to do the null distribution calculation for intensity 1, for intensity 2, for intensity 3. We don't have to do that, which is a good sign. But even then, even if you do have to do it only once, it's very time consuming even for one single cell within that null distribution table. So we did that in bunches of 50. We did that in bunches of 50, in blocks of 50. So the thing is, if you do not find out a change at all anywhere here, let's say within the first set of 50 observations, the first 50 steps, first 50 points in time, then we just move on to the next block of 51 to 100. But let's say if we find 17, observation 17, which is a change point, then we restart the algorithm from 70 to 67. So it always is happening. So in that sense, no, there is no restriction on the number of change points. No, not at all. No.
Okay.
Yeah, but that is a good observation. That's more about the implementation side of it. Yes, yes.
Mm-hmm.
That is a very valid observation. I had a question about your talk too. So when you talked about the TIs that you found, so those were defined prior to the experiment, prior to your study?
Yes, yes.
Okay. So this is more of a complement to that. Here, that is my goal, finding out those breakpoints. That is precisely my goal. Yes.
Yeah, exactly. I first detect the breakpoints, and then by having them, I apply the estimator to estimate the parameters and do forecast.
So you mentioned something about a large T. What was that all about? So was that entire thing asymptotic?
Yes, and this is set that the number of individual units is fixed. So n is fixed, and we have large sample size. So that's why it's called seemingly unrelated regression models. And yeah, I need that for the asymptotic part. I'm using the large T asymptotic.
I see. Let's take another quick look at. So if you have a question, be sure to unmute yourself, or you can stop sharing. Let's take a look at the chat box. Nothing over there. Yeah, but you can totally unmute yourself and ask your question. Probably I should put this one up. case somebody's wondering. Shehnaz, I was curious about your method being applied beyond regression. Have you thought of possible ways in which it can be applied beyond regression? The key idea that you had in your paper was some kind of an averaging, right, between two types of estimators. So did you ever wonder how far can you push that kind of an idea? Can it be pushed beyond regression too?
That's a great point. No, actually, I haven't thought about that in that direction, but it's a good question.
Yeah, because what I talked about was entirely regression free. I did not have any covariates at all. It was entirely regression free. But that is some place that I need to branch into sooner or later. Someday I need to go into cases with covariates. Yeah. We're still available for questions. If you have any burning questions for either of us,
I want
you're all
to say
ears.
thank you, and I have to leave.
Okay.
Midnight.
Me too. Me too. Yes, there is a keynote in about 10 minutes about humans and machines. So if you want, you can totally take a break, stretch your legs, and be there on that link. But we both will be here if there are any last-minute questions. Do you teach these things, Shehnaz, in class?
Not right now, because I thought the undergrad level.
It's too advanced for them.
Yeah.
For the undergrads, yes.
Yeah, but once I move to grad level, yeah, why not? How about you? Do you teach any of this in your class?
No, but here we can, the good thing is we can develop our own courses. So someday we can do that. Someday I can propose a course on point process. But here the closest thing that I have to a point process is a time series. So I teach time series, but that is similar to what you did in discrete time. You're sampling time discretely, but what I talked about, it's entirely continuous and continuous time. You can have an earthquake anytime you want. You don't need to wait for the end of the month to have an earthquake. So this entirely, but I mean, there are still connections. If you look at the inter-event times, and those are a discrete time problem. If you measure the time between two earthquakes or between two financial crashes and index it on that index, then that is a discrete time problem. So there are connections, but predominantly I work on continuous time problems. Yeah. Which again, it could be a little problematic to teach in a class.
Yeah.
But yeah.
Are you going back in person for fall?
That is a good question. We are probably going to go back to a hybrid framework. So we normally have hybrid classes here where some of the students are in class even during normal times when we do not have COVID, even during normal times, because most of them have jobs. So if you want, you can come to class, but you can also stay back. You can attend classes through the internet. So that's the normal model we have here. But yeah, I think we have to go back to that model. Yes. So for us, for the faculty, yeah, we need to go to class. We need to go to class. But for students, they can either come to class or they can stay back. Oh, they can stay back. Yeah.
Yeah, it's good they have the option to choose from.
Yeah, this is because most of the grad classes we do, they are pretty late in the evening. It's once a week, but pretty late, about 2.5 hours. So that is pretty big. So they have their jobs during the day, and during the evening they come to study. How about you? Online or offline in the fall?
Yeah, it's going to be in person, but we do have also the option for students if they wanted to take it online, they can. I mean, some of the classes, it has two sections. One section is fully online for those students that prefer to have online session, and some are fully in person. Yeah, for me, it's in person. I mean, mainly the classes are in person, but there are also online sessions available as well.
Which format do you like?
So in person is better,
Yes, me
and
too.
in terms
Yes.
of interaction with the students, you
Yes.
can see them.
That is true. Yeah.
Yeah.
That is true. Yes. We'll wait a little more. And then we will go to that keynote. You're teaching during the summer?
No. Do you have any class?
No, this is just our time for research.
Yeah.
All right, I think we don't need to wait any longer, right?
Yeah.
It's almost time, and the title also says cancelled. So if somebody can see that, they will find that it's cancelled.
Yeah.
So let's call it a day. So it was wonderful meeting you, Shanaz. Learned
Thank
quite
you.
a
It
lot.
was nice to see you as well.
Yeah, and we'll meet again someday, some other conference.
Have a
Bye-bye.
wonderful rest of the day. Bye bye.
Bye-bye. Bye-bye.